In this video, we will solve a simple scaling problem. If you want, you can pause the video here and attempt to solve for x1, x2, and x3. So let's get started. So in this first model, we input 50 moles. And in the second model, we input 5,000 mole. This may happen if first you do a small scale test just to prove your idea works, and then after you proved your concept, you would go for a larger scale. And so we went from 50 to 5,000. That's 100 times increase. And whenever we do scaling, our composition would always remain the same, because 50 times 0.3 is the number of moles of X going in. 5,000 times 0.3 is the number of moles of X going in. Likewise, 50 times 0.7 is the number of moles of Y going in. And 5,000 times 0.7 is the number of moles of Y going in. So our composition would always remain the same. That's why this is 1/3, 2/3, 1/3, 2/3. And so we just want to solve for x1, x2, and x3. So we went from 50 to 5,000, which is 100 times. So 15 to x1 would be 100 times also. So x1 would be, 15, 100 times is you just add 2 zeros. So 50 to 5,000, you add 2 zeros. 15 would be 2 zeros. Likewise, you do x2. Now with x2 and x3, it's not a composition because it's pure moles of X and pure moles of Y. So composition is whenever you see moles of X per mole or moles of Y per mole. But here we have a pure composition. This is as though it's like an x1 or like a 5,000. So x2 would be similar to this. You just add 2 zeros. Finally, x3 would be the exact same thing. 25, you add 2 zeros. And if you want, you can even check. So 50 times 0.3 is equal to 15 times 1/3 plus 10. So that is our X balance. And 50 times 0.7 is equal to 15 times 2/3 plus 25. And in order to test this idea, do the exact same thing for this one. 5,000 times 0.3 is equal to 1,500 times 1/3 plus 1,000. Likewise, 5,000 times 0.7 is equal to 1,500 times 2/3 plus 2,500. And that's all you need to do for scaling.